Quadratic equations are fundamental in algebra, and understanding how to visualize them helps us solve them. This is the standard form of a quadratic equation where a, b, and c are constants and a is not equal to 0. This algebraic expression represents a parabola when graphed. Let's visualize a specific example. Y equals x squared minus 2x minus 3. This equation creates a parabola that opens upward because the coefficient of x squared is positive. The x-intercepts of this parabola are the points where the curve crosses the x-axis, meaning where y equals 0. These intercepts represent the solutions or roots of the equation x squared minus 2x minus 3 equals 0. Since we can identify the roots as -1 and +3, we can rewrite this quadratic equation in factored form. This is one method of solving quadratics when the roots are rational numbers. Each factor corresponds directly to a root. When x equals -1, the first factor becomes 0, and when x equals +3, the second factor becomes 0. This makes the entire expression equal to 0, confirming our solutions. However, factoring only works easily for certain quadratics. Many equations don't have simple factors or nice rational roots, which is why we need a more general approach like the quadratic formula. Consider this new equation, y equals x squared plus x plus 1. Unlike our previous example, this quadratic can't be easily factored because it doesn't have rational roots. Looking at its graph, we can see that this parabola never crosses the x-axis. This means the equation x squared plus x plus 1 equals 0 has no real number solutions. The roots are complex numbers, which we can't visualize on this coordinate plane. The vertex of this parabola is at the point -0.5, 0.75. Since the y-coordinate of the vertex is positive and the parabola opens upward, the curve will always stay above the x-axis, confirming there are no real roots. This is where the quadratic formula becomes essential. It gives us a direct method to find all possible roots of any quadratic equation, whether they're real or complex, without having to rely on factoring. The graphical perspective helps us understand why we need the quadratic formula. When a quadratic is easily factored, we can find roots through factoring. But for quadratics with irrational or complex roots, we need a more powerful and general solution method. We start with the standard form of a quadratic equation, ax squared plus bx plus c equals 0. This is the form we need to identify the key components of our equation. In this standard form, a represents the coefficient of x squared, b represents the coefficient of x, and c is our constant term. Identifying these values correctly is crucial for using the quadratic formula. Our first step in deriving the formula is to isolate the variable terms. We do this by subtracting c from both sides of the equation, which gives us a x squared plus bx equals -c. Next, we divide every term by a to normalize the coefficient of x squared to 1. This gives us x squared plus b over a times x equals -c over a. This step simplifies our work with the squared term. Now we use the completing the square method. To make the left side a perfect square trinomial, we add the square of half the coefficient of x to both sides. That's adding the term b over 2a squared to both sides of the equation. The left side is now a perfect square that can be factored as x plus b over 2a squared. Remember that a perfect square trinomial follows the pattern first term squared plus twice the product of the first and second terms plus the second term squared. On the right side, we need to find a common denominator. We have b squared over 4a squared minus c over a. Converting the second fraction gives us b squared minus 4ac all over 4a squared. This expression under the square root is called the discriminant. Taking the square root of both sides of the equation gives us x plus b over 2a equals plus or minus the square root of b squared minus 4ac all over 2a. Notice the plus minus symbol in red. This is why we get two solutions from a quadratic equation. To isolate x, we subtract b over 2a from both sides. This gives us x equals -b over 2a plus or minus the square root of b squared minus 4ac all over 2a. Each part of this expression has important mathematical meaning. Finally, we can simplify our expression by using a common denominator. This gives us the standard form of the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all over 2a. The red plus minus sign indicates that we have two potential solutions. This powerful formula works for solving any quadratic equation. The beauty of it is that once you know the values of a, b, and c from your original equation, you can simply plug them into this formula to find the solutions without going through all these steps each time. The quadratic formula is a cornerstone of algebra that we derive through completing the square. When the discriminant, that's b squared minus 4ac, is positive, we get two real solutions. When it's 0, we get one repeated solution, and when it's negative, we get complex solutions. Let's work through a specific example to see how we can analyze a quadratic equation and determine its roots. Here we have the quadratic equation 2x² plus 3x minus 5 equals 0. This is already in the standard form that we need for our analysis. For any quadratic equation in the form ax² plus bx plus c equals 0, we need to identify the values of a, b, and c to apply the quadratic formula later. Looking at our equation, we can identify that a equals 2, which is the coefficient of x² highlighted in blue. The coefficient b equals 3, shown in green, which is the coefficient of x. And finally, c equals negative 5, highlighted in red, which is our constant term. Before applying the quadratic formula, it's helpful to calculate the discriminant. The discriminant tells us important information about the nature of the roots, whether they're real or complex, and if real, whether they're distinct or repeated. The discriminant is calculated using the formula b squared minus 4ac. This expression appears under the square root in the quadratic formula, and its value determines the nature of the solutions. Let's substitute our values from the equation. b equals 3, a equals 2, and c equals negative 5. So we have 3 squared minus 4 times 2 times negative 5. First, let's evaluate 3 squared, which equals 9. So our expression becomes 9 minus 4 times 2 times negative 5. Now we multiply 2 and negative 5 inside the parentheses. 2 times negative 5 equals negative 10. So our expression becomes 9 minus 4 times negative 10. When we multiply 4 by negative 10, we get negative 40. However, since we're subtracting this negative number, the operation becomes addition. 9 minus negative 40 equals 9 plus 40. Finally, we add 9 and 40 to get a discriminant value of 49. This is a perfect square, which will be helpful when we apply the quadratic formula. Since our discriminant is 49, which is positive, we can conclude that this quadratic equation has two distinct real roots. The positive discriminant tells us that the graph of this quadratic function crosses the x-axis at exactly 2 points. Understanding how to find and interpret the discriminant is a crucial step in solving quadratic equations. The discriminant gives us immediate insight into the nature of the solutions before we even solve for the values of x. In our example, we identified the coefficients a equals 2, b equals 3, and c equals negative 5, and calculated a discriminant of 49. This positive discriminant confirms that the equation 2x² plus 3x minus 5 equals 0 has two distinct real solutions. Let's explore how to solve quadratic equations using the quadratic formula. This powerful method works for any quadratic equation, no matter how complex the coefficients might be. Step 1. We need to identify the coefficients in our quadratic equation. Looking at 2x² plus 3x minus 5 equals 0, we can see that a equals 2, which is the coefficient of x², b equals 3, which is the coefficient of x, and c equals negative 5, which is our constant term. Step 2. Now we calculate the discriminant, which is b² minus 4ac. This tells us about the nature of our solutions. Substituting our values, we get 3 squared minus 4 times 2 times negative 5. That's 9 plus 40, which equals 49. Since our discriminant is positive, we'll have two distinct real solutions. Step 3. Next, we substitute our values into the quadratic formula x equals negative b plus or minus the square root of the discriminant, all divided by 2a. Using our values, we get negative 3 plus or minus the square root of 49, all divided by 2 times 2. Since the square root of 49 is 7, this simplifies to negative 3 plus or minus 7, all divided by 4. Step 4. Finally, we calculate both solutions by evaluating the formula with both the plus and minus operations. For our first solution, we have negative 3 plus 7, which is 4, divided by 4, giving us exactly 1. For our second solution, we have negative 3 minus 7, which is negative 10, divided by 4, giving us negative 2.5. These two values, x equals 1 and x equals negative 2.5, are the roots of our quadratic equation. Let's visualize this quadratic equation on a graph to see what these solutions represent geometrically. The roots we found are the exact points where the parabola crosses the x-axis. Here's our coordinate system, where we'll graph the quadratic function f of x equals 2x squared plus 3x minus 5. Notice that the equation matches the standard form ax squared plus bx plus c. The shape of this curve is a parabola opening upward because the coefficient of x squared is positive. When f of x equals 0, we have our quadratic equation 2x squared plus 3x minus 5 equals 0. These points where the parabola crosses the x-axis are precisely the solutions we found using the quadratic formula. Notice how our solutions x equals 1 and x equals negative 2.5 are exactly where the parabola intersects the x-axis. These points are called the roots or zeros of the function. At these specific x values, the y value of our function becomes 0, which is why they solve our original equation. The quadratic formula is powerful because it works for any quadratic equation. The solutions it gives us always correspond to where the parabola crosses the x-axis, whether that's at 2 points like we see here, at 1 point in the case of a repeated root, or at no points when the discriminant is negative and the parabola doesn't cross the x-axis at all.